In today's lesson, we're going to be solving some polynomial equations. You've done this many times before with quadratic equations. We haven't really done much beyond second or third degree equations, but we are going to go beyond that today. If you had something like this to solve, 5x squared plus 3x equals 0, first you'd look for a GCF, which you do have. You have an x. If you factor an x out, that's going to leave you 5x plus 3. And at this point, you'd set each factor separately equal to 0. So x equals 0. On this, you'd have 5x plus 3 equals 0. 5x equals negative 3. So x equals negative 3/5. So you get two separate answers, x equals 0 and x equals negative 3/5. And at this point, we know that that's where this equation will cross the x-axis. We've been calling those guys the roots. So this is a second degree polynomial because there are two roots. So in general, we're going to start solving these, but in higher powers. But the process stays the same. We're going to put the polynomial equation in standard form. What that means is you need descending powers of x set equal to 0. You're going to factor completely. You're going to do the GCF or the difference of squares or the trinomial factor or factor by grouping. We're going to see some more of that. It's been a while since we've done that. The difference in sum of cubes, which is what we did yesterday. We're going to set each factor equal to 0, and then we're going to solve. Sometimes you'll have to do the square root method. Sometimes you'll have to maybe do the quadratic formula or complete the square if the side that you're working on is not factorable. So let's go on to example 2. State the degree of each polynomial below, then find the values of x for which it satisfies the equation algebraically. So because this is raised x to the 4th, we're going to say the degree is the 4th degree. And we're going to try to factor this. Now, there is no GCF. 16 doesn't have any x's, so there's no GCF. So we have to try to factor this. If we try, we know we need two numbers that multiply into x to the 4th. Let's try x squared times x squared. The signs are the same. They're both negative, so minus, minus. And I need two factors of 16 that add up to 8, which would be 4 and 4. So our original equation broke down to x squared minus 4 times x squared minus 4. You have to set each one of those equal to 0. Some of you might say, oh, that looks like the difference of two perfect squares. So you could do x plus 2 times x minus 2, getting x equals negative 2 and x equals 2. On this side, some of you might think about getting x squared minus 4 equal to 0 and then doing the square root method. X squared equals 4. When you take the square root of that, though, x is going to equal plus or minus 2. So it's the same on both sides. I just wanted to show two different methods of getting the answers. Now, what that means is we're done. We have x equals 2, x equals 2, x equals negative 2, and x equals negative 2. We have 4 solutions to this. But even though we have 4, we really only have 2 unique solutions. Because x equals 2 shows up twice, we're going to say that that answer has a multiplicity of 2 because it showed up twice. The same way with the negative 2's. That one's also going to have a multiplicity of 2 since it showed up twice. The multiplicity of the root is the number of times a 0 results in a given polynomial equation. All right, on the next page, this one starts with x to the 6th, so the degree is to the 6th. So we could have up to 6 different roots. We could have this graph crossing the x-axis up to 6 times. Well, this one does have a GCF. That's x to the 4th. When you factor out x to the 4th, you're left with x to the 2nd minus 2x plus 1. Now, you need to see if that x squared minus 2x plus 1 can be factored some more. If not, you'd have to try the quadratic formula or complete the square. Lucky for us, this one does factor. We have x minus 1 and x minus 1. When we solve this, we get x to the fourth equals 0, but when we take the fourth root of each side, we find out that x equals 0. We have x equals 1, and we have x equals 1. Now, we only got 3 separate answers, but these two were the same, and this started out as x to the fourth, so we really got 0 as an answer 4 times. So x equals 0 has a multiplicity of 4, since it was x to the fourth power. Because these two answers showed up twice, we're going to say x equals 1, and that one's going to have a multiplicity of 2, because that one showed up twice. You should try example C right now. The first step of factoring has already been done for you. Please finish that one and check your answers on Schoology. Okay, so what we're going to say is a polynomial function of degree n has at most, and this is really, really important, at most n real roots. We're not talking about imaginary roots, we're talking about real roots. Now, we could have less, and that would be due to the multiplicity. Or some maybe imaginary roots, which we're not going to see today, but you could have imaginary roots. So the most it can have is n. If it's degree 5, the most it could have is 5 real roots. If it's degree 3, the most it could have is 3 real roots. All right, let's take a look at example number 3. If we get this set equal to 0, we have x to the fourth minus 13x squared plus 36 equals 0. And again, I'm starting with an x to the fourth. To get an x to the fourth, I'm probably going to need an x squared and an x squared. The signs are the same. They're both negative, so minus, minus. And factors of 36 that add up to 13 are 9 and 4. Now, what results is 2 factors, but both of those are the difference of 2 perfect squares. X squared minus 9 makes x plus 3 times x minus 3. X squared minus 4 is x plus 2 times x minus 2. And when we go to set these factors equal to 0, we're going to have x equals negative 3, x equals 3, x equals negative 2, and x equals 2. We end up getting 4 real roots. And because each of these only showed up once, the multiplicity of each of these equals 1. Next, I want to go to example 5 because that has 4 terms in it. So the factoring is going to be a little bit different. There's no common term. Unfortunately, that 2 constant has no x in it, so we don't have any GCF. If you remember back to the beginning of the year when we started doing factoring, we learned a type of factoring called factor by grouping. So if you remember, we factor the first 2 together, we put the second 2 together. Then we do factoring separately on both of those. If you look at my first set of parentheses, what's the GCF of those 2? Oh, it's 9x squared. When I GCF that out of my first parentheses, I'm left with x squared minus 2. No, I'm not. I lied. When I factor out the GCF, I have 9x squared. Inside, I'm left with just x minus 2. Sorry about that. In the second group, there's not a GCF, but because this starts with a negative, I have to take out a negative 1. And so when I divide those terms by negative 1 to find out what's left, I should end up with x minus 2 equals 0. If you remember, when you're factor by grouping, when you get your first set of factoring done, these 2 things have to match. If those didn't match, something went wrong. So the ones that got kicked out and the ones that got brought out in front make their first factor, 9x squared minus 1. The ones that matched make the second factor, x minus 2 equals 0. This is the difference of 2 perfect squares. That would be 3x plus 1 and 3x minus 1. This one would be x minus 2 with no work to be done. So this side's x equals 2. This one's going to result in x equals negative 1/3, and this one's going to result in x equals 1/3.